Because of the law of conservation of energy, we know that energy cannot be created or destroyed. Instead, energy is conserved and is constantly changing from one form to another. Energy is also continually being transferred to and from its surroundings, which makes it a crucial part of our daily lives. Believe it or not, energy actually plays a role when you are deciding what you should wear, depending on the weather conditions. A bulky coat would provide a protective layer that would limit the amount of energy that is being transferred away from your body, which results in keeping you warm. Wearing white or light colors during the summertime helps reflect energy that is being emitted from the sun, which keeps the body cool during the heat of the summer. Conduction is an energy transfer process. The New Dictionary of Cultural Literacy defines conduction as a transfer of heat between two parts of a stationary system caused by temperature difference between the parts. In order for conduction to occur, direct contact must be made between the objects that are transferring energy. Conduction can occur between solids, liquids, or gases, but it has been proven to be most efficient in solids. The reason being, the molecules of solids are packed more closely together than they are in liquids or gases, according to Garcia. There are several factors that affect the rate of conduction. These factors include temperature difference between the systems, the length or size of the objects, the cross-sectional area, and the material. As long as there is a difference in temperature between the objects, energy will flow. The energy will not cease until the objects have reached an equilibrium temperature. According to Gonzalez, the further apart the two objects are, the more energy that will be required to complete the transfer. If the objects are larger in size or take up more area, more energy will be required to complete the transfer. He also shares that the greater surface area will contribute to a greater loss of energy in the form of heat. Lastly, he mentions the material used on the objects plays a crucial role in how efficient the process will be. Some materials have proven to be better conductors than others. For example, metal is a great conductor and gets hot very easily. The equation used to calculate the rate of conduction is Q over T equals K times A times T1 minus T2 all divided by D, where Q divided by T represents the rate of transfer, K denotes the thermal conductivity barrier, A is the surface area, T1 minus T2 indicates the difference in temperature, and D signifies the thickness of the barrier. Conduction occurs around us all of the time, whether we realize it or not. A classic example of this type of transfer is cooking on a stove. Conduction is essential in cooking because it destroys harmful bacteria, which makes food safe to consume, according to Fulmer. When a stove eye is heated up, conduction occurs when the skillet makes contact with the eye. Because the skillet, before it is placed on the eye, is cool, it creates a temperature difference between the eye and the skillet. The energy from the burner is then transferred to the bottom of the skillet. And according to Fulmer, as the pan begins to warm up, it absorbs the energy and its molecules begin to vibrate. Then, when the food is placed in the hot skillet, conduction takes place once again, this time from the bottom of the skillet to the new contents, being the food. In a sense, this example is a case of double conduction. Another great example of conduction is when an ice cube is placed in someone's hand. Energy is transferred in the form of heat from the hand directly to the ice cube. In response to the transfer, the ice will undergo a phase change. The ice's phase change includes a change from a solid ice cube to liquid water. Energy is also transferred from the ice to the hand. and this is the reason that the hand is left feeling cold. Yet another classic example of convection is walking across pavement and burning your feet. The black pavement attracts rays from the sun, and the surface becomes warm from these waves radiating from the sun to the pavement. When you walk from, say, cool grass onto black pavement, your feet can become very hot, and if left on long enough, can actually burn. This event occurs because the feet are cool from walking on the grass, and they are moved to the asphalt, which is significantly warmer, and this creates temperature difference. This temperature difference and the direct contact initiate the process of conduction. The next process we're going to discuss is convection. Unlike conduction, convection does not require the objects involved in the transfer to be physically touching. The New Dictionary of Cultural Literacy defines convection as the transfer of heat by the circulation of movement of the heated parts of a fluid. A fluid can be either a liquid or a gas, and fluids have the tendency to rise when the temperature is increased. Convection occurs due to a difference in density. The difference in density takes place because the cooler fluid is more dense than the warmer fluid, and therefore the cooler fluid sits below the less dense warm fluid. According to our book, College Physics, this type of energy transfer can occur naturally or can be forced. An example of a natural convection is the airflow near a beach, whereas an example of a forced convection could be a ceiling fan. The formula used to calculate the rate of convection is Q over T equals Hc times A times Ts minus Tf, where Q over T is the heat transferred per unit time, Hc denotes the convection heat transfer coefficient, A represents the heat transfer minus the transfer area of surface, Ts signifies the temperature of the surface, and Tf indicates the temperature of the fluid. One example of convection is boiling water. This is also an example of a heat transfer. When water boils in a pot on a stove, several steps occur. First, the eye is heated on the stove and transfers heat to the bottom of a pot through conduction. Next, the heat is transferred to the water from the pot through convection. The water closest to the bottom of the pot will begin to warm up first, and as it heats up, it will begin to rise, according to Rutley. Because of gravity, the molecules continue this exchange, evenly warming all of the liquid in the pot. An example of a natural occurrence of convection is an oceanic circulation. According to Kirchhoff, convection drives the Gulf Stream and other currents that turn over and mix up the waters in the world's oceans. For this to happen, cold water must travel down from the poles from higher altitudes and settle at the ocean's floor. Warm water is then pulled down toward the equator. The lighter and less dense warm water rises to the surface of the ocean. The warm water is then pulled north to replace the cold water. Kirchhoff also states that this process distributes heat and soluble nutrients around the world. A prime example of convection is a hot air balloon. According to an article called Physics Steelmaking, this phenomenon of a hot air balloon can be explained solely by the phrase, hot air rises. Convection carries energy from a hot part of a fluid to a cooler part. In a hot air balloon, the pilot heats the air in the balloon. As the air's temperature increases, the balloon will expand, and in turn, the density of the balloon will drop. The balloon will have a tendency to float on top of the denser cool air, and this results in the balloon rising up into the sky. The air next will expand, and some will actually be pushed out of the balloon. According to this article, the end result of this will be that the balloon will be less dense than the cool air outside of it. The last process that we will discuss is radiation. Much like convection and unlike conduction, direct contact is not a requirement of radiation. The New Dictionary of Cultural Literacy defines radiation as the process in which energy is emitted as particles or waves. Our book, College Physics, makes the statement, all objects radiate energy continuously in the form of electromagnetic waves due to the thermal vibrations of their molecules. The rate at which these objects radiate is proportional to Stefan's law, which is stated as P equals sigma times A times E times T to the fourth power, where P represents power in watts or joules, sigma denotes the Stefan-Boltzmann constant, which is 5.6696 times T to the negative eighth power. A signifies the surface area. E is the constant called emissivity that varies between 0 and 1, and T indicates temperature, usually measured in Kelvin. Just as objects lose energy due to radiation, they also absorb it. The net energy gained or lost by an object due to radiation can be calculated using the formula P net equals sigma times A times E times T to the fourth power minus initial T to the fourth power. A natural form of radiation comes from the sun. According to our book, College Physics, the sun is also a near-perfect example of a black body. The book defines a black body as an object that absorbs all the light radiation incident on it. The graph provided shows the solar radiation spectrum, starting with the sunlight at the top of the atmosphere, which is the highest, then to the black body spectrum, ending with the radiation at sea level. It also provides the wavelength and the spectral radiation. The sun also gives off ultraviolet light, or UV rays, and this light is a type of electromagnetic radiation. These waves are what cause nice-looking suntans or pesky sunburns. According to Lucas, a sunburn is the human body's defense mechanism against overexposure to damaging UV rays. Repetitive overexposure to these waves can eventually result in skin cancer. Our next example of radiation is a microwave oven. In order for food to be warmed up, the microwaves produced by the microwave oven must pass through the food. When a wave is sent to the food, it hits a water molecule, and the molecule absorbs it according to Bagley. This molecule then, that has absorbed the wave, becomes excited, and Bagley states that this excitement means that it moves faster and the water heats up. Since the water molecules in the food are heating up, the heat will eventually spread and the rest of the food will become warm. Microwave ovens heat the water within the food so it heats up quicker and more evenly, which is why microwaves are so effective and efficient. Our last example of radiation is warming up next to a campfire. This is a form of thermal radiation, which consists of electromagnetic waves, mostly infrared waves and visible light, emitted by an object due to its temperature, according to Bayard. Through this type of radiation, the energy is converted to heat. According to Bayard, the thermal radiation spreads in all directions. Because it spreads in all directions, anyone standing close to or around the fire will receive its warmth and inevitably become